right, should we get started? So we have two main topics for today. They are Bayesian networks and Bayesian methods in machine learning. And the Bayesian in each case are not particularly related, just a coincidence. And they're really intros. So Bayesian networks is one of the prime topics of one of the sequels to this course, the 1005 course taught by David Sontag traditionally. And then I'm not sure if there's a Bayesian statistics class coming up, but that could very well be its own class as well. But hopefully you'll get a flavor. And at the very least, a big part of Bayesian networks is it's almost a language or notation for describing probability distributions. So at the very least, I want you to be familiar with this notation and kind of the core ideas of conditional independence. Oh, big influx. OK. All right. So Bayesian networks fall into the area of probabilistic reasoning. Probabilistic reasoning is where we represent our system of interest by random variables. So our usual system of interest has features and labels. So if we could represent this entirely probabilistically, where the features and the label are, all of them are random variables. And we think about the whole system as a set of random variables. And somehow or another, suppose we have, what do we need to know about random variables to completely understand them? We need to know their joint distribution. So suppose, whether it's by running experiments in the lab or doing machine learning, or somehow or another, we come up with this joint distribution describing how all the random variables are related. Then we come to, we can do things called inference. And inference on a set of random variables on a probabilistic system is basically making queries about the system. So for example, you could ask, given d elements, d random variables, you could say, all right, well, what's the most likely value of x1, one of those elements? That'd be a very simple query. Another, maybe a little bit more interesting, is what's the most likely value of x1 given that I have this observation of x2? Right? x2 is equal to the value 1. I've observed that. Give me a most likely value of x1. Give me the distribution of x1. So these types of questions are inference. You could ask for the joint distribution of two of them given the rest. Any question you can ask of the joint distribution, these are questions of inference. And the problem of coming up with that joint distribution, we won't really, that's learning, right? That's the thing that we've talked about a lot this semester. So in the context of probability distributions, figuring out what that distribution is, that's the learning part. And then asking questions about the distribution, like parts of the distribution, some random variables given observations of others, that's the inference. So learning and inference. All right, so quick example, medical diagnosis. So we have a random variable for every symptom you could have. You could have coughing, sweating, sneezing, shaking. We can have a random variable for every disease, cold, bronchitis, pneumonia, whatever. And then we could present a question of inference, which is given the observation of three of these symptoms, cough, fever, but not vomiting. All right, fine. What's the conditional on those observations? What's the probability this person has pneumonia? And if we had the full joint distribution, we could calculate that probability and use this as a tool to assist in diagnosis. So this was very popular to do, not as much these days, but going back 15 plus years or more. They built a system like that with 600 diseases and 4,000 symptoms. And in some contexts, it worked quite well. OK. So that's kind of the type of thing we're going to be talking about for the first part of today. So just a bit of notation that we'll be using. We're restricting to discrete random variables today. And this is notation that's very traditional, although we haven't used it in this class, which is that we'll use uppercase letters for random variables, and we'll use the lowercase letters for the values that those random variables take. You've seen that before, right? That's kind of almost classic. So this sort of thing. Big x1 equals little x1. OK. Great. So how do we represent a probability distribution? In the discrete case, in some sense, it's trivial. We just can write down every possible combination of random variables that can occur. And then we write down the probability of that combination. And we make a giant table, potentially giant table, of all the different possibilities. So here's two tables, one for temperature, one for weather. We'll say temperature can be hot or cold. Weather can be sun or rain. And we've described each of these two distributions by tables with the two different values they can take, the probability of each. So the probability of sun is 0.6, probability of rain is 0.4. Fine. So these are called marginal distributions in the sense that we're describing the distributions of temperature and weather independently of each other, right? It's just, if we didn't observe weather, what's the distribution of temperature? If we didn't observe temperature, what's the distribution of weather? To do any kind of inference, like you observe the weather, let's try to guess what the temperature is, we're going to need obviously some distribution on how the two things relate to each other. So the marginals aren't enough. That's where the joint distribution comes in. So here's a joint distribution table. So now it's 2 times 2 is 4 different possibilities for the two variables in conjunction. And we have the probability of each of those combinations. And of course, so they sum to 1, no problem. So given this table, this is the full joint distribution of the two variables. So now this should be able to support finding the answer to any question we may have involving these variables. So if it's hot outside, what's the probability that it's sunny? If it's not raining, what's the probability that it's cold? You know, we can, just by manipulating these numbers in some very elementary way, we can answer any queries that we want from this joint table. Okay. So let's talk a little bit about whether this is actually a realistic way to go. So suppose we have some binary random variables, we have d of them, and then the question is, how many parameters do we need to represent the full conditional probability distribution for d binary random variables? That's my question to you guys. Say again? 2 pi? Yes, I agree. 2 power d, basically. Any slight modification of that? Yeah, 2 to the d power minus 1. Why? Because we have 2 to the d, yes, we have 2 to the d possible combinations of d variables. If they each can take 2 values, great, so that's the 2 to the d. And each of those combinations has a probability. Those probabilities have to sum to 1. So we can really leave off one of those parameters and still represent the distribution. Great, so 2 to the d. So that's exponentially many parameters needed to represent the full kind of unrestricted joint distribution on d variables. That, in many cases, is just too many. So for instance, in the diagnosis case, there were 4,600, if you combine the symptoms and the diseases, there are 4,600 random variables. They were binary, yeah, so that's like 10 to the 1,000 rows or something, which, yeah, that's too many, right? Okay. So this is clearly infeasible, but in general, having a huge number of parameters, it's going to be hard even for storage. But if we can store it, it's going to be hard for computation. And for statistics, we have to estimate those parameters. So imagine how much data you need to estimate, like 100 billion parameters or something. Okay. Point is, we want to get away from this needing exponentially many parameters to represent our distribution. So this is a situation that's kind of like, I really want to draw the connection between this and hypothesis spaces, where you can imagine we're pulling a distribution from a set of possible distributions, which you could think of as like a hypothesis space. And just like in learning, where we wanted to control the size of our hypothesis space to trade off between overfitting and underfitting, we want to do a similar thing here with probability distributions. So if we allow every possible probability distribution, which is exponentially many parameters we have to determine, then this is a huge hypothesis space, and we want to figure out what are natural ways to constrain it. Okay, so how do we restrict the set of probability distributions? Standard way is to make independence assumptions. So if we have d random variables, we're going to say, all right, certain ones of these random variables are independent of each other, or perhaps they're conditionally independent, which we'll come to momentarily. So first, let's talk about the extreme case of mutual independence. So you could say, all right, we have d random variables, and I want to assume that they're all independent, mutually independent. So what's the definition of that? It should be very familiar. You take the joint distribution, probability distribution function, or density if this were continuous, but we're in the discrete case, so these are probability mass functions. You take any possible setting of your d variables, and you compute their joint probability, and that should equal to the probability of the marginal, the product of the marginal probabilities of each of the individual variables. Right? Very familiar definition. So if this is the set of distributions we're allowing, the ones in which the d random variables are independent, then how many parameters would it take to represent such a probability distribution? These are binary random variables. D, because we'll need one for each random variable. Great. Is it d or d minus 1? D, good, right. Because they don't sum to 1. These are independent probabilities. Yes, great. OK. So at one extreme, we have 2 to the d minus 1 parameters. At the other extreme, we have d. So now we're going to look for something that's in between. How do we go between huge and small? OK. Let's skip that. All right, so now comes kind of the key idea for Bayesian networks, which is the notion of conditional independence. So first, there's an equivalent notion of independence, which is actually maybe more intuitive. So this says that the conditional distribution of x given y is just equal to the marginal distribution of x. So you can understand this as you observe y, but your knowledge of x doesn't change. It's as though you never observed y in the first place. So that's a very intuitive way to think about independence. So in this you can derive directly from the definition of independence. Very simple. OK. So conditional independence. Let's take an example to make it a bit concrete. Suppose there are 3 events, 3 random variables. The grass is wet, the road is slippery, and it's raining. So there's clearly relations between these variables, right? If it's raining, the grass will be wet. OK. So they're not independent. Raining implies the grass is wet and the road is slippery. We'll assume that. It sounds like a reasonable assumption. But what if we observe that the grass is wet? Does that give us any information about the road being slippery? Yes? No? I see some nods.
Yes.
You're going to go with yes. Why? So would it make it, if you observe the grass is wet, would it make it more or less likely to you that the road is slippery? More like, yeah. Because if the grass is wet, well, yeah, OK, then there's some chance that it was raining. And if it was raining, then we know the road is slippery. So there's some information transfer. Yeah, agreed. So if the grass is wet, it's more likely that the road is slippery. OK. Great. So on the other hand, suppose we know that it's raining. And then someone tells you that the grass is wet. Does that give you any additional information about the road being slippery or not? OK, so we all agree that it's raining outside. That's common information. Now, I tell one of you folks that the grass is wet. Does this person have any additional information about the road being slippery? Not really, because all the information that one gains from the grass being wet is that it's more likely that it was raining. But everyone already knows that it is raining. So there's no gain from learning that the grass was wet. And so there's no new information about the road being slippery in this simple model. So, okay. Ah, yes, that's true. So, so there could be another random variable in our world, which I didn't introduce, which is someone's watering the grass. In that case, well,
so if the grass is wet and it's raining, then you know that the road might be.
well, I think in this case, okay, I think I will agree with you that there's probably a way to make the problem so that that they won't be independent. But in this setup,
Okay, so you thought it's no reason for grass being wet.
yeah, this is a very restricted world. Yeah. All right. So if you know R, if knowing R means that W and S are suddenly independent, then that's called conditional independence. And you write this W orthogonal sign S condition on R. So given R, W and S are independent. Formal definition, it's pretty intuitive. It's just like the factorization you get for independence, except we have a condition on R at every piece. So condition on W and S are conditionally independent given R. If probability of WS is equal to probability of W times probability of S, where all those probabilities are conditioned on R. So it's just like independence, except for in every piece we're conditioning on this event. Okay? All right. So suppose we have conditional independence. Does that imply that we have independence? No. Okay. Right. That was the example we just gave. The wet grass and the road. Because they are not independent, but they're conditionally independent. All right, what about the other way? What is the other way? I forgot already. Does independence imply conditional independence?
Yes.
You think yes? Okay, we'll see. Now, no. All right, let's try to write down this world in probability distribution in math. So we start with the joint distribution of the three events, W, S, and R. The first thing I've written makes no assumptions about independence at all, or conditional independence. This is simply definition of conditionals. So I've broken out R, and then I multiply by the probability of R, and this is an equality with no assumptions. All right, but now let's assume, as we agreed is reasonable, that W and S are conditionally independent given R. So then I can break this term up into two pieces, like this. Is this clear? Not if it's clear. Okay, great, thank you. All right, so I claim this is in between. How many parameters to specify this joint distribution with these assumptions? How many to specify probability of W given R? I hear it too. Sold. All right, so R can take two different values, yes and no, rain or not rain. If it's raining, we need to figure out the probability that it's wet. If it's not raining, we need to figure out another probability that it's wet. So we have the probability of wet given that it's raining and the probability that it's wet given that it's not raining. That's two different parameters that we can set. All right? All right, I see a few nods, great. Same for probability of S is slippery given R, and probability of R is just one parameter, so how many total? 5, great. So we had, how many for full independence? For full independence, we have 3. We have one parameter for each of these variables. For unrestricted, any possible, no independence at all. That's the 2 to the d minus 1, 7, right. And this in between thing, 5. Great. So this is an example of our moderating the complexity of our possible distribution from full, no assumptions, the full possible joint, all possible joint distributions to the most restrictive, completely independent. Great. Any questions about this? Yes? Oh, OK. That was just how many possible combinations of W, S, and R are there? That's the first question. 8. There's 8, exactly. And each one of those gets its own probability. So that's 8. Yeah. Except the sum of those 8 probabilities has to be 1. So you really don't need one of those. You only have 7 that you can set freely, and the 8th is determined. So it's really 7 parameters. Good? OK. So that's like 2 to the d minus 1. Yeah. OK, great. All right, so that's our warm-up on conditional independence and how we control the complexity of probability distributions. And now we're going to introduce a little bit of kind of a notation or a language. It's Bayesian networks. So Bayesian networks are used to specify joint probability distributions that have a particular factorization. And as we saw, factorization corresponds generally to independence, conditional independence relations or independence relations. Here's an example of a Bayesian network. It's a Bayesian network. We have 4 random variables. Each is drawn as a node in a graph, C, H, A, and I. And then there's these directed edges between the nodes. And these encode, we'll see that they encode some conditional independence assumptions. But for now, what they tell us is just how our joint distribution factorizes. So here is the joint distribution of C, H, A, and I, 4 variables. And it breaks up into pieces in a way that you'll learn in a second how to read from this graph. So any node that doesn't have any parents, a parent of a node is something that has an edge pointed to it. So the parents of H are C and A, great. And C has no parents. OK, so the probability of C is written without any conditioning. Probability of A, the same way. The probability of H given CA is a factor because H has the parents C and A. And similarly, I has a parent A, so there's a factor for that. So I've made no claims. I've only told you so far that there's a way to translate this picture into this factorization. And now we'll give the formal definition. So first of all, a directed graph, which is the picture that we're going to discuss, has things. Each of these things are called nodes, and then each of these arrows is called an edge or directed edge in our case. All right. Some terminology you can check out later. The descendants of a node are all its children, its children's children, etc. The non-descendants, quite clear. It's all the nodes that are not the descendant of a particular node. So the non-descendants of 3 would be what? Well, 1 and 2, yeah. 4 and 5 are the descendants, so 1 and 2 are the non-descendants, yeah.
Will there be a cycle in our graphs? Like 1 depends on 2, 4 depends on 2.
So, OK, so you're asking, is there a dependency cycle in this graph? Is it? OK, so good question. So if you ignore the direction of the edges, then this is a cycle. That's correct. That's right. If you account for the direction of the edges, then this is not a directed cycle. A directed cycle would require that as you traverse the cycle, all the edges are pointing in the direction that you're moving.
I didn't mean in this setting, but in our general setting, graph for the Bayesian network, does it require to be acyclic?
Yes. Don't worry about it. OK. A directed acyclic graph, also known as a DAG, is a directed graph with no directed cycles. Great. So, okay, we just discussed this would, whoa. So here we have, if you follow the direction of these edges, we go in a cycle that respects the direction of the edges. So that's a directed cycle. This is not a directed acyclic graph. Acyclic means, yeah, no cycles. Okay. All right. So yes, or rather, yes or no to your question. We do not allow directed cycles in the graphs corresponding to a Bayesian network. It's DAGs, acyclic. Yeah. What will happen if there's a directed cycle? Then it will not be a Bayesian network. Okay. Are you asking if you wrote down, if you tried to write down this type of factorization, given respecting the a cycle graph? Well, what will happen is you'll have something on the left. Why don't you? That's a good question. Why don't you play with that, and you can report back on it. It's a good question. Okay. Yeah.
This graph is like an assumption between about the relationship of the random variables, or how do we determine which are the relationship? Do we have to do statistical tests?
Yeah. So, okay. So we're coming to a yeah. So how does one write down decide on this acyclic graph, the graph structure, because that encodes these independence things, and yeah, this is a modeling assumption. This is you imposing your idea on how you want to model the random variables, and it's a kind of a trade-off between what you think is happening and what the more what we'll see is that the more kind of the sparser your graph, the easier the graph is to deal with, the Bayesian network is to deal with, the fewer the parameters there are, for instance. So maybe you don't have enough data, or you don't have the computational power to learn a model with too much complexity, with too many dependencies. So it's kind of it's a modeling choice. Yeah. Hi.
Will there be two variables that are mutually dependent by each other?
Can there be two variables that are mutually independent?
Yeah.
Sure. Okay. So can you have entirely disconnected components in your graph is the question?
Yeah.
Yes, you can.
Maybe there is each have two directions. There are two nodes and they have edges to each other.
You can't have two nodes with edges to each other because that would make a cycle, a directed cycle.
Yeah,
And
so could you please give an example of this kind of variables?
give an example of variables.
Or under what conditions?
We don't allow the directed cycles, so.
Yeah, I know, but I mean that this kind of
The restriction of being directed acyclic graph, when would that apply?
yeah.
Yeah, that's what we're talking about. Yeah. Okay. So this is a formalization of what I described to you. The joint distribution factorizes so that probability of xi only xi only enters in via a term that has the conditioning based on its parents. So this describes the factorization of the joint distribution on these random variables. Okay. Just the immediate parents. Yeah, parents are just immediate parents, not otherwise it would be like ancestors or something. Yeah. That's what makes things very simple. That's right. Yeah. Okay. All right, so now we're going to talk about the most basic types of conditional independencies that we see encoded in graphs and get a feel for them. And I think this will come to your question of some examples. All right, so here's a network which we've actually described. This is a good one for the wet grass example. So we have 3 nodes, A, B, and C, with directed edges pointing down from C to A and to B. And that corresponds to this type of factorization, right? Just from the definition of Bayesian network. Clear? All right. So now let's ask some questions. Let's ask whether A and B are independent. So do you think A and B are independent in this graph? Oh, fair answer. All right, so let's assign some interpretation to these variables. Let's say C is rain, A is slippery, you know, the road is slippery, and B is the grass is wet, just like in our first example. All right, so let's just work out the math. So probability, the joint of A and B, so that's this variable and this variable. If these are independent, how should this factorize? PA comma B equals P of A times P of B. That would be independence. So this would have to be true for all values of A and B. Well, we could try. So we can start with the joint ABC, probability of ABC, and marginalize out over C, which would mean sum over the possibilities. So I've taken this, that's the joint, and I've written sum over C, and I got stuck because this doesn't simplify. This, you can't get rid of, in a general case, you can't get rid of this. We can't simplify this probability of C, it doesn't go away, and we can't reduce it down to PA, PB. So did I prove it? Not quite, but this would be something you could do in a specific case on your homework or something, for example. Okay, so P of A and B are not independent in general. But now suppose we condition on C, we observe C, like that. All right, now let's do the same thing. So now P of A and B given C, if we have conditional independence, now what should happen? This equals what? Yes, P of A given C times P of B given C. That would be the conditional independence. Great. So here's the joint divided by P of C. This is nothing but definition of conditional probability. So nothing's happened so far. Good. Now let's plug in this factorization, which is implied by the Bayesian network assumption. And you see what will happen when we plug this in for PABC? See what happens? Yeah, this PC cancels with this PC, and we're left with PA given C times PB given C, which proves the conditional independence of A and B given C. So, did we prove anything? Yeah, in this case we did. Okay. So I won't put this on the homework. Maybe I will. I have a habit of that. Okay. Case 2, indirect effects. So it's like this is called a chain structure. A leads to C leads to B. It's actually a Markov chain. So the factorization implied is that P of A without parents, P of C given A, and PB given C. This is the factorization implied by the Bayesian network. All right, independence. So this would be, here's my example. A is raining. That leads to the ground being wet, which leads to mud being on your shoes. Okay? All right. So are A and B independent? That's the question. You think not independent. A and B are not independent. All right, let's check. So P of A given B, that's the joint A, B, and C where we marginalize out over C. That's fine. Let's substitute in this expression for the joint. Can you see what's going to happen? What do we need to happen if they are independent? This has to equal what? PA times P of B. Okay. So when we sum this thing out over C, we're going to have to get P of A times P of B. All right, let's see what happens. So the PA comes out from the sum over C, because it has nothing to do with C. And we're left with this. And what does that reduce to? C given A, sum. Say again? So so the question is, does that equal P of B? All right, so no, we're blocked, can't be. So A and B are not independent, which makes sense. That was our guess, initial guess, right? Very good. So now the next question is, what if we observed C? Then are they independent? And what do you think? All right. Yeah, so you can trace this through. You can prove this rigorously, that the factorization applies, so we will have conditional independence of A and B given C. Great. Third example, common effect. All right, so now we have A and B both leading to C. All right, so what's an example? So A could be like, how difficult is the course? B could be how knowledgeable you are about the material, and C could be like the final grade. And it's kind of clear that you have to look at both of these things to figure out the final grade. Right? So that's why they're both leading in. All right. So independence. Do we think A and B are independent? Yeah, marginally I would say they are independent. And yes, we can show this directly from the factorization. Now how about if we observe C? Are they independent then? So C is the grade. So we all know someone's grade, and then we find out how hard the course was. Does that tell us any more information about how knowledgeable they were, more than the grade told us in the first place? That's kind of the question. So whether the interpretation makes sense or not, mathematically, if we observe C, then A and B are not dependent. OK, so that's kind of interesting. So if we want to know information about B, and we observe C, we could still get even more information by observing A also. Is that right? You see that? Because B and A are not independent given C. So if I didn't observe C and someone told me A, I know nothing. But if someone tells me A and if someone tells me C and then they tell me A, then I can get some information from A because I know C. OK. Great. All right. So yeah, question? All right. So those are kind of a few standard types of independence that we look for, that we have in graphs, in Bayesian networks. We won't get into it in this class, but there's ways to, using just graph algorithms, to directly read off from a graph all the conditional independence relationships between the various nodes. All right. So that's called, there's a notion of d-separation. You can look that up if you'd like. Kind of interesting. Certainly it'll be covered in the inference class next semester if you take that. OK. So one thing we do want to ask, though, is there's some kind of a notion of if we want to get information about, here, what's the letter I want to use? So suppose we're interested in a single variable A that we don't have any observations of. And we have this huge Bayesian network with, say, thousands of variables, some of which we can observe, some of which we can't. And the question is, if we want to get the most possible information about A, do we have to observe all the variables in the graph? And what we've already started to see is the answer is no, right? Because there's these conditional independence relations. After you observe certain things, other things become irrelevant. You get no new information. So the question is, what would be the minimal number of nodes we can observe to get the maximum amount of information possible so that we don't have to observe anything more? Is that a clear idea? So that concept, that thing is called the Markov blanket. All right? So here's what it would be mathematically. So the distribution of A given all other nodes in your graph is equal to the distribution of A given the Markov blanket of A, which one hopes is a lot smaller, much smaller subset of the nodes. And given just this subset of nodes observed, you've gotten all the information you could possibly get from all the nodes in the graph. OK. So here's a picture of what that Markov blanket looks like. So here's A. And it turns out, all right, so how would you describe the nodes that we need connected to A? We certainly would need the parents of A, right? Because those give very direct information about A. How about the children of A? Sure, the children of A can often gives a lot of information about A, right? Anything else? Say again? the parents of the children of A. Why is that? Because of the common cause thing, exactly. So this is exactly the case where you need the parent of the children. So we want to know everything we can about A. We know the child C, we need that for sure. So we can still get information out of B because A and B are not conditionally independent given C. So the Markov blanket, and I guess there's a theorem about this, but we've seen it pretty much. The Markov blanket of A is the parents of A, the children of A, and what's called the co-parents of A, which are exactly the parents of the children of A. Great. Yes? So the question is, are the grandparents relevant? And the question and the claim is no. Yeah, well, okay. What if a grandparent is also a co-parent? Is that possible? Is that possible? All right. So in that case, I think that would not be the case. Oh yeah. So if the grandparent, yes. If the grandparent is not a parent, if the grandparent is not a child, if the grandparent is not a co-parent, absolutely. Please. Yeah, the Markov blanket is everything under this nice blue blanket. So this and this are the parents, these two, okay? These are not. These are grandparents that are not co-parents or anything. So this and this are on the blanket. These two are on the blanket because they're children. This is in the blanket because it's the parent of a child. Same with this. And this and this and this and this are not in the Markov blanket. Is this clear? Cool. All right. Okay. So let me give a first example of a Bayesian network that people actually use in machine learning. It's probably the simplest model. It's called naive Bayes. I think Levent will talk about it in more detail tomorrow, but I'll just sketch out the picture for you. So naive Bayes, this is actually binary naive Bayes example. So the network structure, the Bayes net structure looks like this, where Y, now we're kind of want to be in a machine learning setting, so Y is like our label, but it's a random variable, and we'll say that it's binary. And x1 through x4, these are also random variables, but we're going to think of those as like features, and we'll say those are also binary. So one possible, would be a possible application of this, suppose we want to have a prediction of whether a news article is about sports. Okay, so yes or no, that's binary. That could be our label Y. And then x1 through x4, these could be like, I don't know, the first 4 words of the title of the article. No, excuse me. These x1 through x4 could be features such as, is the word soccer in the title? Is the word ball in the title? Is the word etc. So each of these 4 random variables represent some binary description of the article. And then we can make a probability distribution, which would be like, well, what do we need to specify for this naive Bayes, for this Bayesian network? How many parameters would we need to specify this Bayesian network? Think about it. 8, 4, 5. Okay, let's break it out. So each of these things is conditioned on Y. So first consider the Y equals 0 case. For Y equals 0, we need the probability that x1 is 1, x2 is 1, x3 is 1, x4 is 1. So we have 4 parameters for the Y equals 1 case, and 4 parameters for the Y equals 0 case. So we have 8 that we need to specify this distribution. So again, I left one out. The probability of Y itself. Excellent. Lost one. So what's the actual correct answer? 9. Great. So we need the probability of Y, and then the conditional probabilities of x given Y for each of the x's. and every possible assignment of y. Good job. Okay, so here's the joint distribution factorizing according to the Bayes net. And yeah, that was the one that I forgot about. And then there's these 8 from all the conditionals. Excellent. Okay. So independence-wise, this encodes the idea that these 4 features are conditionally independent given the class label y, which is an odd assumption for something like text, where words are not independent. Certain words usually come together and these sorts of things. But that's the assumption in naive Bayes, which is actually a pretty commonly used model. How might you learn this model? Just suppose I gave you a whole stack of articles with the types of features we had, and I told you these are in sports and these are not in sports. How could I, for instance, estimate P of y? That's a good starting point. I have a random sample of articles. I give them to you. They're all labeled sports and not sports. How would you estimate P of y? Yeah, you could just count how many ones are about sports and how many are not, and you could get an empirical probability of y being sports. That's fine, great. How about probability of x1 given y? Suppose x1 is, title has the word soccer in it. Yeah, you just count. So you could say, all right, in the y equals sports case, how many articles have the word soccer? And from that, you estimate one of these parameters, and same for the not sports case. So these models are very easy to learn. They're very easy to estimate the parameters of if you have the full data. All right. All right, so we have a few more minutes, so I'm going to show you just a couple more kind of classic models that you can learn about. Yeah?
These examples that you have been giving are all discrete random variables.
Yeah, it's true.
What in the case of continuous random variables?
So the question is, everything I've said is discrete. Am I being sneaky? Is something scary or interesting happening in the continuous case? And the answer is that all these notions of conditional independence and stuff, they still apply for continuous variables. Sometimes it's more difficult to work with them and sometimes not. So there's a very classic model that's coming to my mind, which is called the Kalman filter. And these are all continuous observation. All the variables are Gaussian random variables, so they're all continuous. And so that's certainly, so I'll point that out in the next slide. Yeah?
Question about this one is why is that we want to see all the square variables is dependence of y, but not inversely, like in a common factors or common results, common outcomes, like from x1, x2, x3, x4 to y.
Okay, so you're asking, what if we had the arrows pointing from x to y?
Yeah.
Yeah, so that's a thing. That actually is a model that we've dealt with. In fact, it was problem 7 on the test. These are conditional probability models. Condition on x, having observed x, what's the predicted distribution of y? Exactly. So if you flipped all the arrows and had the x's pointing to y's, that's exactly the scenario that we spoke about, I think, in the previous lecture, where we want to predict the distribution or density for y, having observed x. So that is exactly that case. Yeah. Something becomes a lot harder in that case, though. So the one thing we didn't do in the previous lecture is that we never estimated this marginal distribution of the x's, right? We never found out what the distribution of just x is. What's the probability of this set of features, right? But note here, we're finding the probability. We can figure out the probability of just the x's. How can we figure out the marginal probability of x2? We just get rid of y. We have the conditional distribution of x2. We can get rid of, we can find out the marginal by bringing in the probability of y. So if we flip the arrows, the way we've treated it before is we only cared about the conditional distribution of y given x. We could also ask for the full joint distribution of x and y with the arrows flipped, but we haven't worked with that. Yeah?
This thing that we do with testing like this, like we are going to calculate probability of y given x. I mean, typically the right hand side will have probability of y.
Yeah, so we're assuming the model, that we're assuming the data are generated like this. The joint distribution factorizes like this. And then in application, we're going to observe x's. And then we're going to say, what's the conditional distribution of y given x? But that is not the same as reversing the arrows. Because reversing the arrows is talking about conditional independence relations and how things factorize. You can always ask, no matter what these arrows say, we could have connections between the x's and stuff. We could still ask, what's the distribution of y given x? Okay. All right. Say again? Conditioned on y, the x's are independent. Otherwise, good question. Are they, without any observations, are the x's independent or not? Say again?
Can't say like, we couldn't factor it.
Okay, but that was no. Yeah, we didn't prove it, but yeah, no. So without observing y, the x's are potentially dependent. Yeah. Why would that be? Because if you observe, we don't know what y is, but the first word is sports or soccer, then that makes it much more likely that the second word or another word would be score or something. So that's how there's dependence between the x's. Yes?
Are the x's conditionally independent or just independent?
Great question. Yeah, they're conditionally independent, but not independent. Good. Yeah?
It seems like as the number of variables that you use grows, it grows very, very quickly, right? Faster than 2 to the power.
Say what? Can you repeat that again?
The number of DAGs for n variables.
The number of possible Bayesian networks, let's say, or DAGs for a certain number of variables grows faster than exponentially.
Yeah, so that seems like a difficult learning problem.
Oh, we don't try to, well, some people do try to learn the DAG itself. But for now, let's assume that we write down the DAG, we write down the conditional independent structure. We kind of try a few. We try one that makes sense to us. Maybe we vary it a little bit. But yeah, the learning problem is quite difficult if you want to try to learn the structure. Yeah.
And it's harder than writing down the joint.
Harder than writing down the full joint?
Yeah.
You mean because there's more of them?
Yeah. No? I guess the joint describes everything, so that doesn't make sense.
It's certainly, yeah, right. It's certainly not harder than allowing the full joint distribution, but yeah, I mean, usually if you have a lot of variables, you don't dream of trying to search over the space of all possible, or if you do, you're doing it in a very kind of regimented way, like maybe deciding on one edge at a time whether you add it or not or something. It would be to find the global optimal structures definitely seems intractable. Yeah. All right, should we take a break then? Okay. All right, how many of you guys have heard of Markov chains? Who has not heard of a Markov chain? You don't have to raise your hands. All right, Markov chain. We've seen one already. It's a simple structure. It's kind of one of the favorites of an intro stochastic process class. So here we have a sequence of random variables. It could go on forever. X1, X2, X3. And this is our Bayesian network structure for it. So a Markov chain is a Bayes network, Bayesnet. So we can read off exactly the form that the the joint distribution factorizes as, right? So we need X1 has no parents, so we need a marginal distribution for X1. Often in a Markov chain, you'll fix a special state with a certain, that it always starts in that distribution and it transitions from there. Different ways to handle it. And then the distribution of X2 given, or rather the X3 given its history is just conditioned on X2. So everything only can be written in the whole joint can be written in terms of factors in which the current variable only depends on its immediate parent. So that's how the Markov chain factorizes. So each of these conditional distributions, like x2 given x1, x3 given x2, in this context, it's called a transition model because we can look at this almost as a time series. And a Markov chain is often used in a time series context where the index is increasing over time, for example. So this could be observation at time 1, observation at time 2, etc. So the conditional distributions are called the transition model. And then as we've written it here, each of these transitions could have a different probability distribution, right? But if the probability distribution is the same when we go from x2 to x3 as when we go from x3 to x4, that's called time homogeneous. It means the same at all times. And that simplifies the model quite a lot. So at the bottom, I've drawn an example of what we could have as a state transition distribution. So in this case, we have 4 states. What's that mean? Each of these xi's can have 4 different possible variables. These random variables could take 4 values, S1 through S4. And then here I've drawn up what's state transition matrix, or essentially. So S1 can, if x1 is S1, then x2 can be S1 with probability 0.3. It can be S2 probability 0.7. And that's it. From S1, we can only end up in S1 or S2. Is this clear? From S2, we can end up in S3 with probability 0.4 or S4 with probability 0.6. Now look, there's an arrow pointing backwards. Is this a problem? Does this violate our Bayes net assumption? Yeah, OK. Yes and no. No. If this were supposed to be a Bayes net, then yes, this would violate the assumption. This is not supposed to be a Bayes net. This is just representing transition probabilities. OK. So this is not a DAG, but then that's OK, because it's not a Bayes net. Yeah. Yeah, OK. So if x1 has value s1, then there's a probability that x2 also has the same value s1. And that probability is 0.3. So this describes how this graph here describes how the state changes as we go from one state to the next one in line. And the transition probabilities between all the states. Yeah?
Is it only xi given xi minus in the transition?
Yes. What do you have in mind?
Like here we have S2, S4.
So these are not histories. S1, S2, S3, S4, these are 4 possible values of the random variable. So the S's could be like, I don't know. Someone presents a flower to us, one after another, one flower. And the observation is the color of the flower. Red, green, yellow, blue. And maybe there's some pattern to the way they're presenting the flowers to us. And so if someone shows us a red flower, there's a 50% chance that the next flower will also be red. So the transition from red to red is 50%. Yes?
So then 0.7, for example, from S1 to S2
Yeah.
means like probability of P of x2 condition on x1.
Exactly. Yes. So probability of x2 being equal to s2, like red, given that x1 is equal to s1, like green, is 0.7. Okay. All right. So this is a Markov chain. So this forms the backbone of what's called a hidden Markov model, which is a very interesting model. In this case, we have this Bayesian net structure. And what typically happens here is that the x's are observed and the z's are not observed. The z's are hidden variables, they're like latent variables. All right. So I'll try to come up with an example in a moment, but first let's see how this factorizes just based on the Bayes net structure. So it has 2 pieces. First of all, anytime an x1 shows up, it's only going to be in a term with x1 given z1, because that's what the Bayes net says. So here are all those terms. These are called it's called the observation model because it's all the terms involving the x's, which are the variables that we observe in the hidden Markov model. So these factorize and we can collect them together into a product of observations given the z's. Now what's left are the z's, when the z's are on the left-hand side here. And based on this model, so what are the parents of z2? The parents of z2 is only z1. x2 is not a parent of z2. So when we write down the factor involving z2, it will only be probability of z2 given z1 and no x's. Okay? Similarly, the parents of x are only the z right above it. So anytime an x shows up on the left, it's conditioned only on the z right above it. Yeah? This is a Bayesian, yeah, this is a Bayesian network. That's right. Yeah, so we can understand Markov models and hidden Markov models as Bayesian networks. And when you draw down this graph, you know exactly how the joint distribution factorizes. That's right. Yeah. So one special case of a hidden Markov model, to get to your continuous thing, is called a common filter. Common filter is a hidden Markov model where all of these observations, all the distributions relating the x to the z and the z's to the z's are, call them linear Gaussians. So basically, x1 given z1 is a Gaussian distribution, and its mean is dependent on some linear function of z1. Okay? And z2 given z1, z2 condition on z1 is Gaussian, where its value is has a mean that's a linear function of its parent, its value. So this would be a continuous Bayesian network that has a lot of use in practice. So when would a common filter be used in practice? Here's an example. Suppose you have some radar system and you're trying to track the motion of an airplane in space. Okay? We can represent the state of the airplane using, I think 6 variables would be typical. X, Y, and Z to represent its position, and X, Y, and Z to represent its current velocity, right? All right, so if we know the position and the velocity, and we want to see where it is in 1 second, we can use simple physics. Suppose it's an object that's just flying in outer space, so there's no acceleration, for simplicity, okay? So we can just multiply the velocity times the time and add it to the position and get the new position. And the velocity would be the same if there's no acceleration. So using physics, we've described how the state transitions from one time to the next. Is that clear? So all that I've described, I'm going to call z's. Z's are the states. Because we don't have perfect observation of that position and velocity. We have a noisy observation using our equipment. So given the airplane is at a particular position with a particular velocity, and now we have an observation of that airplane, which say is that position and velocity plus some noise. Okay? So perhaps it's Gaussian noise. So x1 in that case would be like z1 plus Gaussian noise. And that's what we end up observing. So we observe a lot of x's, which are states of the airplane with noise. And what we would like to go back and estimate is the actual position. And what's interesting is because all the noise is independent in this model, at least in this model, we can actually share some information between these observations that will help us smooth out our predictions of z. So if we did not have these arrows between the z's, between the positions of the airplane, then we can only use our observation at time 1 to help us figure out what was where the true state was at time 1. But because there's dependence between time 1 and time 2, we can also use our observation at time 2 to help us figure out exactly where it was at time 1. Let's see if we can believe that from the graphical model structure. So the question is, our z1, what is the question? We've observed x1, and then we observe x2. And the question is, does x2 give us any more information about z1 once we already observe x1? Okay, so our x1, and so how would you say it? What's the independence? Well, first what's the question, and then what's the answer? So what are we asking? Is there independence between what and what?
Z1 given x2.
Yeah, exactly. So are z1 and x2 independent given x1? So if we observe x1 and then we observe x2, do we get any additional information about z1? And the answer is no, they're not independent. If we observe x1 and we get x2, observe 2, we get more information about z1, right? So that dependence that's in this model allows us to share information across the observations, and that's that's called smoothing, where we can get better estimates of the z's by using all the information. Yeah. So what is the Markov blanket of z1? So there's no parents, and so the children of z1 are x1 and z2. That's right. And and there's no co-parents. Okay. So the Markov blanket of z1 is x1 and z2. That's true. Agreed. So if we observed everything in the Markov blanket, then it would be independent of everything else. If we observe the Markov blanket, then z1 is indeed independent of x2. But we do not observe the Markov blanket because we don't observe z2.
Okay.
So we don't have a Markov blanket situation here.
Can you explain again?
Yeah, okay, sure. So the question was, wait a second, x2 is not in the Markov blanket of z1. So why do we want to observe x2? And I said, well, yeah, actually, you're right. The Markov blanket of z1 is just x1 and z2. This I agree. So in fact, if we observed x1 and z2, then x2 would give no additional information about z1. But we do not observe z2. So the Markov blanket doesn't preclude x2 from giving more information. Yeah. Okay. Okay. Yeah, so I guess your general question is, are there other sets of random variables such that if I observe those, I'm independent of everything else? And yeah, sure. You can make other rules like, but we're not in a Markov. But yes, so if we would still have to observe something in the z. There's no way to be independent of all the x's here. So even if we just observe x1 and xt and all the x's in between, xt plus 1 will still give us more information about z1. There's nothing blocking it. Okay, so I'm not sure what the definition of Markov blanket you're going for would be. Okay. All right, so this is hidden Markov model. This is, yes, please.
Yes, okay. In the joint probability distribution, in the left side of the equation, you z1, z2, z3. But there is also x1, x2, x3.
Yeah, I should have included those. Sorry, that should be there. Thank you. Yes, the joint would have both of them. That's absolutely true.
All states.
Yes.
And x.
Yes, 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 yes.
Okay.
Yes. Good catch. Is that clear? I should have written on the left the z's and the x's because we want the joint distribution of all the random variables in our setting. Yeah. Okay. So next is an example where we've flipped the arrows. So here the x's point to the z's, right? This was an idea. So what I've drawn here is called a maximum entropy Markov model. It could also be a conditional random, no, I'll just say maximum entropy Markov model. So notice the arrows are reversed, and here the factorization is, now here I haven't drawn the joint on the left. I haven't been that brave. I've only drawn the conditional distribution of y's given x's. All right, so y's given x's, factorize given x's, the y's are just a Markov chain, and so they factorize like a Markov chain does. Conditional on x. If we wanted to do the joint distribution, what would we have to add in? right, so if I get rid of that condition on x, so where did the, just tell me about the p of x, how does that fit in? Yeah, so yeah, it's straightforward. So we have these. So we have the term for p of y2 given y1, yes. And now we'd also have the term p of y1 given x1, and we'd have the term p of y2 given x2, and p of y3 given x3. Yeah. So we just add in a lot of additional terms that condition on x directly. Yeah. And then we need. Well, that's what we already had. Apologies. Then we need one more piece. Yes, we need the marginal distributions of the x's. That's right, we need to add in, right? P of x1, P of x2, P of x3. Yeah. OK. All right, so any more questions on the Bayesian networks? I just wanted to give you a flavor of some models at the end here. But yeah.
I'm not sure if I understood this right. Like, when the x's are the observed data, whatever we see, right? And then we have some hidden latent variables called y. So usually when we model a Bayesian network, do we model the data or the latent variables or both?
So the question is, do we model the latent variables or what we observe, which we've been calling features? So great question. So in these 2 pages, I've given both versions. So in a hidden Markov model, we model everything. So we would observe x's, and we don't know z's, but we'd like to learn z's. So z's are like labels, x's are like our features almost. They're what we observe. And we model everything. We model a joint distribution on x and z. All right? So this is the first time this course that we've talked about modeling the x's at all. Usually we just take the x as input, and we don't have any description of how the x's were generated, right? We just want to know what's y given x, basically. And that's what's going on also in this maximum entropy model, where, yeah, we could have tried to write down the joint of x and y, but what we do in maximum entropy Markov modeling is we just model the conditional distribution of y's given x's. So we don't actually have any model for what the marginal distribution of the x's are, for example. So here we model everything. Here we just model the conditional distribution of y's given x's. Did that answer your question?
Yeah, I mean, I was just curious to know which pages to write. Like, is it like an empirical decision? Or?
Yeah, I mean, generally, what you'll find is that if you want to have very complicated functions of your features giving rise to your y's, don't try to model your features. You just make a conditional distribution, condition on x, and then you can have very complicated functions given x to give you a lot, depending on different changes in x, you can have lots of different distributions on y. Very complicated functions mapping from x to y. If you model the joint distribution between x and y, it becomes hard to have kind of very complicated functional relations between the values of x and y. It's hard to see it from this setting, but in practice, that's what you'll find. You know.
But your x's are not hidden.
Yeah, x's are not hidden here. Y's are hidden. That's right. X's are observed. Yeah. OK. All right, so we have about half an hour left. And I wanted to give you guys an introduction to Bayesian statistics. So you how many people here have studied something about Bayesian statistics before? Posteriors, priors? Yeah, probably a little more than half. Good. So shouldn't be too, should have a lot of class participation. Should be great. All right. Are you guys ready to switch gears? OK. So Bayesian methods. So to introduce Bayesian methods, first let me recap the opposite of Bayesian, which is frequentist, classical statistics. So in frequentist or classical statistics, which you've probably had in some intro statistics class, we start with a probability model, typically a parametric model, say with a parameter theta in some parameter space, capital theta. This determines a set of probability density functions or mass functions. And we're assuming that a particular distribution from that set produces the data that we observe, or governs our world. So in frequentist statistics, the parameter theta that determines the probability distribution we consider it to be fixed and unknown. And our job as statisticians is to figure out what theta is. And once we know what theta is, we've kind of answered all the questions that we have to answer. So the point of statistics is that we don't know what theta is, but we have some data sampled from the distribution, and going from the data back to an estimate for theta, that's what statistics is all about. Okay. All right. So there's a notion of point estimation in statistics. And so first, the definition of a statistic. I forget if I've mentioned this before. A statistic is any function of our data. So we always represent data with the script D. A statistic is any function of the data. And then, so what's a parameter estimator? So we say a statistic, now I've written theta hat, still a function of D. So it's a statistic still. But now I've intended it to be an estimator for theta, our unknown parameter. So if we have a statistic whose intention is to estimate theta, that's called a point estimator. It's estimating the parameter. And what does point mean? It's a single value. This is as opposed to a confidence interval, which kind of gives an interval for a parameter we don't know. This gives a single point, a single value. That's why it's called a point estimator. All right, so we have point estimators in statistics. So the mean of a bunch of variables is the point estimate for the expected value. That would be the classic example. OK. So point estimators have certain qualities that you want them to have. So one of them is consistency, which basically says if you're drawing data from this distribution and the amount of data goes to infinity, then your point estimator should converge to the parameter it's trying to estimate. Seems reasonable as a thing to desire of a point estimator. So consistency is one. If you get into more advanced statistics classes, you'll talk about efficiency, which is, very roughly speaking, is your point estimator getting to the true parameter value as fast as you can for any given value of n. So in a certain sense, the mean is a more efficient estimator of the expected value than the median, even though for certain distributions, the median and the mean are the same. Okay. Maximum likelihood estimation. Why do we always use maximum likelihood estimation? Well, first of all, it's often straightforward to calculate. But second of all, you can prove that it has these characteristics of being consistent and efficient in a certain sense. So that's why statisticians like MLE. So investigating these sorts of things would be the topic of a intermediate to more advanced statistics class, but I just wanted you to know about the concepts. So in frequentist statistics, it's a lot about inventing estimators and then proving that they have certain properties, like these ones we've just talked about. And in some sense, there's no prescription for how to come up with an estimator. You have to invent one. Anything can be an estimator, but no one's going to use it unless you can demonstrate that it has certain nice properties. So a point estimator could be it's just a statistic. It could be any function of the data. But it's not interesting unless you could prove something about it. So that's the name of the game in frequentist statistics. You're proving things about proposed algorithms for generating estimates and these sorts of things. Is that clear? All right. So this is in contrast to what we'll see in Bayesian statistics. All right. So Bayesian statistics. Similar framework, but it has a new piece. So first, there's a bit of a viewpoint change. In Bayesian statistics, instead of having a parameter that's just a fixed value but unknown, we consider all the unknown parameters to themselves be random variables. All right? And our model that we declare for our system includes that random variable in it. So let's see what that looks like. So the new ingredient is called the prior distribution. And this is basically the marginal distribution that we impose. We come up with it out of our head for the unknown parameter theta. So it's a distribution on the parameter space. We'd like it to somehow reflect our belief of theta when we come into the problem. So for instance, if someone gives you a coin and they say, well, figure out the probability of heads. Well, we have a good prior belief that the probability of heads is going to be something close to a half. Right? We're going to be very surprised if it's 0.9 or something. So our prior might be like, okay, the probability of heads is most likely within a certain small range of a half, but maybe it's small probability that it's really far from a half. It's a weird coin. Anyway, you could code up something like this distribution on theta that describes your belief on what theta is. And of course, it's something you have to write down before you see any data. It's supposed to be uninfluenced by the data. All right. So how does the Bayesian method work? We start with a prior distribution on theta, and then we have the other piece, which we also have in frequentist statistics, which is the likelihood model for the data. So let's look at this closely. So we have some description of the likelihood of a data set D given theta. All right? So we don't know what theta is, but for any given theta, if I tell you, all right, well, for theta equals 0.45, what's the probability of having this sequence of coin flips? Well, we know we can write that down. And we know what we would, that's a very straightforward likelihood model. All right. So in addition to the likelihood model, for Bayesian settings, we have a prior distribution on theta. Very good. OK. So the new thing in Bayesian statistics is after observing the data D, we come up with what's called a posterior distribution, theta given D. All right? So we started with our initial beliefs on what theta would be. For a coin, it's like, we're not entirely sure, but it's pretty tightly centered around a half. And then we observe 1,000 coin flips, and we're going to have a new belief, a posterior distribution on theta, which, if the coin is in fact fair, it's going to be tighter around theta, tighter around a half. OK. So the posterior distribution we'll find is kind of the core element of Bayesian statistics. So let's figure out how we can solve for this. So theta given D, all right, let's just use Bayes' rule. And let's flip around the conditional and write that as D given theta times marginal theta over probability of D. So what do we know here? So P of theta, that's our prior. That we made up. Right? Probability of D given theta, that's the model. That's given a particular theta, we can calculate the likelihood of the data that we saw. That's what would go in here. And this is, well, we can get this just by summing out over theta. But it turns out we actually don't need to calculate this generally. I think if you read that proportionality handout, that would explain it. But I think we'll come to it in a minute. So P of D is called the marginal likelihood of the data. So a good way to remember it is the posterior is proportional to the likelihood times the prior. This will recur. This is kind of the refrain that you keep having in Bayesian statistics. Posterior is likelihood times prior. All right. We hope that the posterior represents. So Bayesian statistics, in a lot of senses, people have written kind of philosophy papers on, should represent perfectly rational reasoning about your state of belief of a system or a parameter or whatever it is. As long as you can precisely code up your initial belief before seeing any data, and you believe your model to be true, your likelihood model, then the rational belief after observing the data is exactly the posterior distribution, is represented by the posterior distribution on theta, in some sense. All right. And then once you've had your updated belief on theta, any action you want to take, throw out the coin, use the coin, bet a certain amount of money that the next flip will be heads, all these decisions should be based on your posterior distribution on theta. All right. So, OK. what about the original question of a point estimator for theta? Right? So that was the frequentist question. We have this theta, it's not known. We come up with a theta hat to estimate what theta is. We come up with different properties we want it to have. So that's frequentist statistics. In Bayesian statistics, what do we end up with? We have our prior, we observe our data, we end up with a posterior distribution on theta. So that's a different kind of object. Now we have a distribution on theta, which represents our like updated beliefs on theta. If we want to actually produce a single number, well, we can introduce a loss function to describe how, is it best to be, do we want to penalize big errors more than little errors? Maybe then we want to use square loss. You could try to find an optimal single value prediction that optimizes some loss function with respect to the posterior. All right. Let's just take a specific example. So coin flipping model. So the parameter is theta, that's the probability of heads. And let's write that as theta, it's in 0 or 1. The parameter space is interval 0, 1. Great. We observe data. It's a sequence of coin flips of heads and tails. We'll assume that the coin flips are IID, and so, or at least let's say they're independent. Yeah, IID. And we can summarize them with the number of heads and the number of tails, right? So we'll write that n sub h and n sub t. Likelihood model. That's going to be given a theta, given a probability of heads, what's the likelihood or the probability of seeing the data that we see? So study this for a moment. So if n sub h is the number of heads, theta is the probability of head, 1 minus theta is the probability of tails, n sub t is the number of tails. This gives us the probability of observing the exact sequence of heads and tail flips that we saw. Okay, so that's the likelihood of the data for a given theta. Okay. So what's the other piece we need in a Bayesian model? The likelihood model, we need the prior. Right. What type of object is the prior in this setting? It's a probability distribution over the set 0, 1, the interval 0, 1. That's right. So what types of probability distributions live on the interval 0, 1? Uniform distribution certainly lives on the set 0, 1. Yes, that would be a fine prior on theta. Any bigger family of distributions? Say again? Beta? Beta distribution is supported on the 0, 1 interval, that's right. Great. So the traditional prior for a finite interval is beta distribution. It's very flexible. Let's see what that looks like. So each of these lines, each of these graphs, is a particular probability density from the beta family of distribution with different parameter settings. So here's one that's symmetric and centered at a half. Is it a half? Right? So that would, if we use that as our prior, that would be saying, I don't think it's more likely to be heads or tails, but I'm not that confident that it's a half. But I think it's more likely to be a half than something else. Right? That's what this distribution would represent. How about this orange one? So, all right, I think this is an unfair coin. The probability of heads is 0.2. It's very unlikely to be, probability of 8 on heads. Okay. This U-shaped one, this is saying it's a really unfair coin. I'm pretty sure it's either always heads or always tails. All right, so that's another beta distribution. All right. So it's a very flexible family of distributions. And you can choose one from this family as your prior. And to jump ahead a little bit, what we'll find is that the posterior distribution on theta will also turn out to be in the beta family, which is very nice. That property where the prior and the posterior are in the same family, that's not always the case, but when it is the case, we say that the family of the prior is a conjugate prior for the likelihood model that we have. Okay. All right, so we could pick a prior. And this is what the density function looks like for the beta. It's proportional to, and that looks a lot like Bernoulli. That looks a lot like the likelihood function, the likelihood model. Just to grasp what these parameters mean, the mean of a beta distribution, that's ht, beta distribution has two parameters, is h over h plus t. So for instance, I called the parameters h and t intentionally for like heads and tails. So if we wanted to say, oh, I think probability of heads is like 3/10, I could say, well, h is 3 and t is 7, and that would give the mean of 3/10. What's the variance? Does anyone know, if I double h and t, what happens to the mean? Yeah, if I scale h and t by the same constant, the mean doesn't change. If anyone knows the beta distribution, what happens to the variance? Does anyone know how the beta distribution is parameterized? Okay. When you increase the scale of h and t, the variance decreases. So if we multiplied h and t both by 10, the mean stays the same, but the variance gets smaller. And so that's like saying we're more confident in that particular mean being the actual value or near the actual value of theta. Okay. All right. So this is something I forget if I work it out here. So this is very easy to work out, but if you have a prior that's beta ht, and we observe some data with n sub h heads and n sub t tails, how do we get the posterior? Well, the posterior is proportional to likelihood times the prior, right? So here we have the likelihood and here we have the prior. So the posterior is proportional to the product of these two things. And you can do this in your head. Can you see what the product looks like? Yeah, it's going to be theta to the nh plus h minus 1, 1 minus theta to the nt plus t minus 1. Okay, so that's the posterior density, like that. Can collect. And this, you can see immediately, this is again a beta distribution, right? Because beta is any density of this form. So what's h for this density? Yeah, h in the posterior is h plus nh, and t is t plus nt. So that's kind of interesting. All right, so I've summarized it here. So this is pretty interpretable, actually. What if we thought of h and t as, you could think of them as, what is the term? You could think of them as like prior counts. So like you're representing your belief in terms of some hypothetical data set that you might have observed beforehand. So if you observed, if you could say, oh, my belief is, it's as though I'd observed 51 heads out of 100 total flips. So your prior would be like h is 51 and your tails is 49. So that would be h and t, would be 51 and 49. And then n sub h and n sub t are the new actual observations that you made. And then your beta gets updated, your distribution gets updated by adding the number of heads and the number of tails you got to the parameter values. Okay. So let's just look at some, yeah?
So will there be a problem if our posterior is not conjugate to prior?
Yeah, so if your prior family, if you've chosen a prior distribution such that when you get the posterior, it's no, in this case, suppose that we're no longer a beta. It's not a problem, it's just more difficult to work with. So when you have conjugate priors, you can often solve in closed form exactly what the posterior distribution is in terms of your data and your prior. But if it's not a conjugate prior, you usually cannot figure out in closed form what the posterior is. And you have to resort to some other method. For instance, often you can find a way to sample from the posterior distribution. And then you could, example, like histogram it up or something. Or compute the mean of the posterior distribution, if that were your goal.
So can we use the data to estimate prior? I mean, just take sample of the data and estimate prior.
You can't, because the idea of the prior is that it's your belief before seeing the data. So if you cheated and just wrote down you looked at the data to figure out your prior, then the posterior no longer represents kind of a rational updating of your belief based on the data. Yeah. Okay. So yeah.
So when you see data and you update your distribution and you get the posterior, the variance diminishes, right?
The hope is that the variance will decrease as you get more data, yeah. So a typical convergence theorem for Bayesian statistics would be that the posterior distribution concentrates on the true value of the parameter. The variance goes to 0. That's right. So here's a quick example. Suppose we put a beta 2-2 prior, right? So this is as though we had 2 heads, 2 tails. It's not that tight. This is our prior distribution. We observe a sequence of heads and tails. Suppose it's 75 heads and 60 tails. All right? So the posterior, all right, so the MLE is 0.556. Great. The posterior distribution is beta 7762, where we've added the actual observations to the 2-2 of the prior. So added 2 to the heads and 2 to the tails. And you can plot that density, and you can see it's much more concentrated now than initially. So there's the variance decreasing as we get data. All right.
So,
Yeah.
in any case, the data MLE is going to be the mean, no matter what prior distribution.
Oh yeah, the MLE has nothing to do with the prior at all. That's correct. The MLE, what is the MLE in this context? What do we have to look at to figure out the MLE?
Probability of data.
Yeah, we need the likelihood model, which tells us the probability of the data given theta. And then we find the theta that gives the highest probability of the data. That's the MLE. Yep. Okay. All right. So we have a few minutes left. So I will tell you the standard ways to get a point estimate for theta in the Bayesian setting. So right now we know how to get a posterior distribution for theta. What are your ideas for how to come up with a single point, a single number that would estimate theta as well as possible? You're pointing to MLE? The peak. Ah, great. The location of the peak. OK. So if you have a density, what's the term for the location of the peak? Nope. 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 Wow. I think I heard it though. Mode, yes. The mode of the distribution is the term for the highest likelihood. Yeah. So the mode of the distribution would be right here. That's right. But there were some other interesting ideas. So what's another thing you could use? Wait, the maximum is, but we just did the mode. The maximum happens at the mode. Another one was? Expected value, you said? Sure. The expected value of this posterior distribution would be a fine estimate. People who are Bayesian tend to prefer the expected value in many situations to the mode. The mode of the distribution, the mode of the posterior, has a special name in Bayesian statistics. Do you know what this is? Have you heard of, yeah, the map, exactly. It's called the map estimator. What does map stand for? Maximum a posteriori, right? It's the maximum of the posterior distribution. MAP, maximum a posteriori. Okay, that's usually the easiest one to figure out. Any other ideas? How you come up with a point estimate for a distribution, of a posterior distribution? We already named the common ones. I'm just seeing if you have any other ideas. What if someone were judging us on how good our estimate was? So someone knows the true value of theta, and we submit to this competition a theta hat. All right? And we want to submit a theta hat that has, let's say the expected performance is as good as possible. What do I mean by performance? So we have to know, they're going to rank people on how good their estimate is of theta. To rank people, you have to have a loss function. We have to have a way to measure how far off theta hat is from theta. So what are some loss functions you could use to measure? You could use square difference between theta and theta hat. If it's square difference, what do you think the optimal theta hat will be? The?
Expected value.
Yeah, so it's the expected value. Using the same type of calculation that you guys did on homework 1, you could show that the theta hat that minimizes the expected square distance between theta hat and the true theta is the expected value of the posterior. Great. Okay. So what else could you use to measure the difference between theta and theta hat? Absolute difference, yeah. In which case, what would you want to take from this posterior distribution? No. What? The median, yeah, would be great. Okay. Yeah. The mode would be optimal, but not in this sort of scenario. The mode would be like, suppose theta is discrete, not continuous. It's a color, red, green, blue, and you need to predict the color, and you only get credit if you get the right color. So it's like a 0-1 type of loss. And you want to maximize your probability that theta hat is correct. So then this is the situation where the mode is optimal. Okay, that said, people use the mode in many other situations as well. Okay, that's good for today. Any last questions? Yeah? All right, ask me after. You guys are free to go. You come up.